attending. My name is Andrei Farcasiu, and I'm a master's student from Carleton University in Canada. Today, I'm happy to present both mine and my supervisor, Dr. Bora Pulatsu's research study, where we showcase a convolutional neural network-based pipeline for the streamlining of Masonry Quality Index analyses. In this presentation, I will provide a concise overview of our computer vision-based pipeline powered by the YOLO convolutional neural network for automatically detecting bricks within masonry assemblies and providing key information with respect to the Masonry Quality Index analysis framework. And I'll also provide special attention to how I trained a YOLO model to detect bricks and how I optimize its performance by tuning its hyperparameters. Furthermore, I will also show how our framework is applied in practice with a case study focusing on a clay masonry building in my hometown of Kemptville, Ontario, just south of Ottawa. First and foremost, I would like to go over the Masonry Quality Index, which our pipeline aims to automate. This is an analysis method that aims to provide preliminary estimations of the material properties of masonry assemblies through visual inspections of their morphological characteristics. There are numerous parameters considered by the MQI, which include brick condition, block size distribution, stone and brick shape, wall and leaf connections, bed joint horizontality, head joint staggering ratios, and mortar properties. While most of these parameters can be determined through visual inspection, our pipeline aims to automatically provide information on the block size distribution and the head joint staggering ratios. So the head joint staggering ratio quantifies the extent of the interlocking of the bricks. This is determined quantitatively by tracing the shortest path from the highest to lowest mortar head joints and dividing it by the length by the distance between the start and end points of the path. And on the other hand, the block size distribution quantifies the largest dimensions of each brick. And the results obtained from both calculations are used to determine whether their respective parameters are not fulfilled, partially fulfilled, or fulfilled, depending on the ranges that they fall under. So going back to our MQI formulation, the level of fulfillment of each parameter is cross-referenced with these numerical values, which are then used by several formulations to provide estimates of material properties. So for example, it is possible to predict elastic moduli and compressive strength values to predict the masonry's behavior against vertical loading. So obtaining MQI parameters by hand is very time-consuming, as you must perform these measurements manually usually. However, our workflow aims to make this process easier with the help of machine learning technology. So, as you know, you only look once. YOLO is a convolutional neural network that is designed to recognize objects within images and videos, and it is able to perform both object detection and instant segmentation simultaneously in single evaluations of the input data. But however, for this study, we used a special implementation of YOLO version 11, which conducts inference tasks on high-resolution images by dividing them into tiles to detect smaller objects more easily and accurately. So in order for a YOLO model to function correctly, it must be trained on an appropriate data set. So for this study, we utilize one called MCRAC 1300, which is a collection of 1,300 images of masonry facades with labels for both bricks and cracks. So these images in the data set are split to serve different functions. So in this case, 1,000 are used for training, 150 for validation, and the rest for testing purposes. Now, as I previously mentioned, I selected this masonry building in my hometown of Kemptville to serve as our case study. To evaluate the accuracy of our YOLO model, I created orthomosaics of two of this building's facades, which provide orthogonally aligned representations of their masonry assemblies. Now, first, I took numerous photographs of the building using both my smartphone and my drone. Then I processed the photos using photogrammetry software, which yielded this sparse cloud, which I then used to generate this dense point cloud, which provides an accurate 3D representation of the building. Then I used a point cloud to generate these two orthomosaics, which are used to evaluate the performance of our YOLO model. Now, while the accuracy of a YOLO model is dependent on the quality of its training data, it can also be improved by tuning hyperparameters optimally. So as such, a model's accuracy is measured, as a lot of people may know, using various metrics such as the reduction in loss or an increase in detections with higher confidence ratios. So for this study, I trained several models iteratively to determine the best combination of hyperparameter values that yield the most masonry bricks detected with a confidence ratio of 90% or above. So the first hyperparameter I adjusted is the number of epochs, which are individual training cycles, which of course people know, where the YOLO model learns from the entire data set. Now, training a model, with the optimal number of epochs can also prevent, overfitting or underfitting from occurring, which, prevents, degradations in accuracy. So in this case, I tried different epoch amounts ranging from 20 to 100, but with the results, as you can see here, it showed that 40 epochs provides the best balance between detected bricks across both orthomosaics. Next, I also adjusted the weight decay, which introduces regularization to prevent overfitting. So it is recommended that the weight decay value remains low when you train a model under smaller batch sizes, which in this case, the default value for YOLO is 16, as doing so for larger sizes can yield poorer results. However, in our case, increasing the weight decay to 0.007 yields the most bricks in both orthophotos. Otherwise, decreasing it yielded poor results, which we imagine that it was due to insufficient regularization. As it is also recommended that the learning rate must be lowered when training under smaller batch sizes, we adjusted that as well. So it is shown that the default value of 0.01 is optimal for detecting the most blocks for the northwestern orthomosaic, while 0.012 yields the most for the southwestern one. Therefore, a learning rate of 0.01 is most optimal for this case study, as it once again provides a better balance between quantity and accuracy. And we also adjusted the batch size as well, of course. However, it is shown that neither increasing nor decreasing the batch size beyond the default value, 16, provides any improvements. Therefore, the optimal batch size remains as it is due to the weight decay and learning rate adjusted specifically for this batch size. Now, training a model with the final combination of hyperparameters yields the following segmentation masks, signifying that it is relatively successful at detecting and delineating the bricks in both orthophotos. Now, and to obtain the staggering ratios from these brick masks, they are processed in an automated pipeline developed by my colleague, Peter Griesbach, who was part of our research group. So the masks are superimposed over a grid of equal-sized cells, where they are assigned a brick based on the overlapping masks. And this process results in a set of rectangular geometries with zero thickness interfaces. And then afterwards, the tool samples head joints along the highest course, and then iteratively scans for the closest head joints in the courses below, providing staggering ratio values. So as such, this pipeline was implemented on our case study, which obtained a collection of staggering ratios as shown here. So for example, for the southwestern elevation, a total of 21 staggering paths were sampled, resulting in ratios ranging from around 1.7 to 2.3, which is well above the threshold of 1.6 for both single and double leaf masonry walls. Therefore, the corresponding MQI parameter is considered to be fulfilled. Similarly, a Python script was developed to obtain bounding boxes of each brick mask, and which were used to extract their widths, which were scaled to real-life dimensions based off of in-situ measurements of the building itself. Now, these scaled widths were then used to obtain these block size distributions, which, for example, for this elevation once again, it shows that most bricks have dimensions larger than 200 millimeters, but less than 400. Therefore, the associated MQI parameter for masonry unit dimensions is considered to be partially fulfilled. So in conclusion, while our YOLO model is shown to be effective, it fails to detect all the bricks found on both facades, because there were still a very, very few missing. Now, this may signify that a new model may need to be trained with better training data or further hyperparameter adjustments. Otherwise, we can also introduce augmentation to artificially expand the data set, which hopefully will provide us more accuracy. In addition, further improvements can introduce the identification of mortar joint thicknesses and the delineation of masonry cracks in order to provide a better digitization of the masonry assembly. So once the pipeline is improved, it will eventually be implemented into a broader workflow that facilitates automated data-driven computational modeling. And if you're interested in seeing that, please read my conference proceeding for my next conference in Lausanne. So until then, I would like to thank you once again for your attention.